Alright, let's do a problem based on the isentropic efficiency we just talked about in the previous video. We talked about the isentropic efficiency of a work consuming device, work producing device, right? So this problem is basically the isentropic efficiency of a compressor. So it's a work consuming device. So if we have a compressor, okay, let's draw a compressor. So this compressor has input and output. So input, it's basically it's saying that a refrigerant of 134A enters an adiabatic compressor. Adiabatic compressor means that there is no heat transfer. As the saturated vapor at 100 kilopascal at a rate of 0.7 meter cube per minute. So the pressure at entrance 100 kilopascal and the mass flow at entrance equals to 0.7 meter cube per minute, and then pressure at exit P2 equals to 1 megapascal. That's what it's saying, that its exit as 1 megapascal. If the isentropic efficiency of the compressor is 87%, so the isentropic efficiency equals to 87%. Determine A, the temperature of the refrigerant at exit of the compressor. So what is the temperature at the exit, right? And B is that power input in kilowatts. So this compressor, it's absorbing the power, right? Or it's a work consuming device. So it says that what is the power input. And then number C is that also shows the process on a TS diagram with respect to the saturation line. So we have to draw a TS diagram and show that what is the process with respect to the saturation line. So first let me write the assumptions for this problem. Excuse me. Assumptions, right? So the first assumption is says that it's an adiabatic compressor. That means no heat transfer. Adiabatic, no heat transfer. No heat transfer. Second thing is that it's a compressor. There is no change in the velocity or no change in the elevation, right? So that means that kinetic energy and potential energy is negligible, or we can neglect them, are negligible. And then the third case is basically saying the device is adiabatic, thus the heat transfer is also we talked about that one. But the third case, or the most important case, is that it's a steady flow process. Why steady flow? We see that there's the constant mass flow, which is 0.7 meter cube per minute. So it's a steady flow, right? It's a steady flow device. So for steady flow device, we derived the equation. So let's write those equation. The first case, or let me write this requirement, right? Required. What are the things it's asking for? First, it's asking for the exit temperature. Exit temp, right? Exit temperature equals to what? TE or T2, whatever you say. B is the power input, and C is the TS diagram, right? So for A, or the exit temperature, we have to use the isentropic efficiency formula. But before that, we would like to get some data of that refrigerant. So for that refrigerant, we have two different cases. One is that entrance pressure, and another is that exit pressure. And then we are saying that this is an isentropic process from this problem, right? So if that's the case, then we'll go ahead and determine some of the thermodynamic properties. So from the refrigerant table, which is the table A12. For table A12 we have state 1, and state 1 pressure is equals to 100 kilo pascal, right? And it's a saturated vapor. So if that's the case, we'll see. Let me show you guys here. Table 18, 8, 13, 13. So this is saturated refrigerant. Yes, saturated refrigerant, and our pressure was 100 kilopascal. So in that 100 kilopascal pressure, we have to get we need to get the value of the HF or the enthalpy, right? HF, HFG, and HG. And also we have to determine the entropy, or we have to get the entropy value. So basically we'll record all of those information along this line, right, which I already did. Um, this is just to show you guys which line and which pressure. So this one, right? And for the saturated vapor, and table is A12. So let me write those conditions. So at H1, right, it's a saturated vapor, so it will be Hg. H1 equals to Hg, which equals to 234.46 kilojoule per kg. And then S1, which is also Sg, right, at 100 kilopascal, it will be 0.95191 kilojoule per kg times Kelvin. And then V1, or specific volume, V1 equals to Vg, which is equals to 0.19255 meter cube per kg, right? So we have all this information about state 1. Let's go for state 2. State 2, we have the pressure at 1 megapascal. And for similarly, if we use the table A13, we'll get, this is the isentropic efficiency. That means that S2S equals to S1. So if we get all those value from table A13, right, table A13, then with respect to the pressure, we'll record the some of the information. Basically we need the enthalpy, H2S. H2S equals to 282 times 0.53 kilojoule per kg. So for the isentropic efficiency, it a compressor, right, isentropic efficiency of a compressor, H2S minus H1 divided by H2A minus H1. Let me write very quickly so then you guys understand, or remember that what is the diagram look like. So if we have two different pressure diagrams, so initially pressure is low and final state pressure is high, then isentropic line is this one. This is entropy line, and this is enthalpy line, right? So isentropic line is this one, but in actual cases it goes like this. That means that the work, isentropic work versus the actual work. So this is isentropic work and this is the actual work, right? So for isentropic work, it's this one minus this one. So isentropic work Ws, and the actual work Wa, which is the top one. So Ws equals to, from clearly we can see that this is H2S, this is H1, and this is H2A, right? So actual isentropic work divided by actual work. So from this, the diagram, we got this definition which we derived in previous video or previous yeah, lecture. So from here, if we plug in all those values, we'll get the, for example, this is 0. So the isentropic efficiency of the compressor was 0.87 equals to isentropic efficiency of the compressor at state 2. We just got it 282.53 minus we got it 234.46 divided by actual H2A. We don't know about that one, H2A, and we know 234.46, right? So if we get H2A, which is equals to, if we solve it, it will be 290,289.71, right? So this is kilojoule per kg. So we know that entropy, actual entropy, enthalpy at exit, right? So using this enthalpy, we will let's go ahead and calculate the temperature. So if we know that enthalpy, and if we know that the pressure, the temperature, actual temperature, so thus for P2A actual equals to 1 megapascal and H2A equals to 289.71, the temperature actual would be 56.5 degree Celsius. So let me show you. So 1 megapascal is 289. So here superheated refrigerant, right? Superheated refrigerant, and we have the pressure 1 megapascal, right, at exit, and we have the enthalpy is, which is equals to 289.71. basically, if we think that its enthalpy line is this one, 289, which is in between these two, right? So if we do the interpolation of this along this line, excuse me, so it will be this line along this line, then it will be in between 50 to 60. So we did the interpolation, which I already did in previously, and that interpolation result is saying that it will be it will be 56.5 degrees Celsius, 56.5 degrees Celsius. So that's the answer, right? Let me color it. So this is the answer A. And then let's do the B, right? So this was for A. So for B, it's asking us that what is the power input of the pump. So the mass flow rate for the refrigerant, mass flow rate, we have that one is m prime equals to 0.7 meter cube per minute, right? So if we want to calculate in kilojoule per kg per second, that means we have to use the specific volume information. So that means it will become mass equals to, so let me convert it, or let me write the definition of the density. We know that density equals to mass divided by volume. So if we convert in specific volume, then the expression will become this, right? So that means that mass equals to specific volume prime times this specific volume, right? So from here the mass, if we convert it, actually if we convert it in specific volume, then it will be specific volume divided by specific volume at state 1. So this one is the specific volume of that liquid one, and what is the specific volume of the liquid or the refrigerant, and this is the specific volume of that condition is state 1, right? So for this one we know that 0.07, it's in meter cube and also in minutes, so we have to convert it in second. So if we want to convert it in second, then it will be, we have to divide it by 60. And then for specific volume at state 1, we recorded it for the pressure 100 kilopascal, which is 0.19255 meter cube per kg, right? So this is meter cube per second, which is, and this is meter cube per kg. So now we'll get this mass equals to kg per meter cube. Okay, let me write the, excuse me, which is, if we solve this will be 0.06059 kg per second, right? So we have the mass now. Now the only inlet and outlet exit, the mass is constant because it's a steady flow. So if the mass is constant, then or the mass flow is constant, then energy balance equation of that system equals to energy in minus energy out equals to total change of energy, right, of that system. So actually if we express it in the rate, right, so this will be for steady flow or steady case, it will be 0, right? So for now, if we rewrite this equation, E in equals to E out, right? So the incoming energy and outgoing energy, it's becoming the same. So then the incoming energy it's basically the power input to run that compressor, right? So W actual times W actual of incoming, right, plus also the incoming energy is coming with that refrigerant, which is M prime of H1. And then the outgoing energy is the energy that was taken by that refrigerant at superheated condition, so which is M H2, right? So if that's the case, then we can calculate the actual energy input, right, for that compressor, which is equals to M prime of H2 minus H1. So we know that all of those value, right? So mass equals to 0.06059 times H2, we got it 289.71 minus 234.46, right? Here one thing guys, this H2 is actual, so how much actual energy is leaving to that system, so I can write it 2A. So that actual energy we just got it from here, 289.71 for state 2. So that's the one we are using in this formula. So WA input, right? So then actual work input for that compressor, it will be 3.35 kilowatt. So that's the answer for part B. Now it's asking us that, what is the, so it asking us that also show the process on a TS diagram with respect to the saturation line. So I think for this part, if we have a, I mean, if we know all those conditions now, if we have a saturation line, then we can show it how it's, this process is happening. So if this is a, if this is the HS diagram, which diagram it's asked, the TS diagram. So TS diagram, pressure versus enthalpy, compressibility. Anyway, so if we do draw a TS diagram, which we did see it in HS diagram. So the TS diagram, the saturation line, if we draw a saturation line, this is liquid phase, right? And this is saturated phase, right? And this is superheated phase. So for this case, we saw that initially the pressure was low, means that 100 kilopascal, and then finally the pressure was 1 megapascal. So this is 100 kilopascal and this is 1 megapascal. So so in these conditions, we saw that the efficiency of that efficiency of that compressor was 87%, right? 87%. And to change this state from 1 to 2, how much energy or how much work input was done, we also calculated, which one is the 3.35 kilowatt. So actually this is, this is something that we have to use the TS diagram, but it's very conceptual for this case. But if I give you the problem, I'll ask for only the temperature or the pressure at inlet or exit, as well as the efficiency or the work done or work consumed by that device. So that's all for the math problem based on the isentropic efficiency of the work consuming device. But if I ask you guys, what is the isentropic efficiency of a work producing device, it will be turbine. And if I ask you for nozzle, you know the formula for nozzle. And if I ask you for the problem for pump, you also know that one. So yeah, keep practicing based on the isentropic efficiencies of a steady flow device, right? We have seen or we have the formula for four different types of device. So I just did one, and rest of the three you guys go ahead and practice those problems. So that's all for this class, and again, thank you for watching this video, and we'll meet in next class and we'll talk about new topic. Thank you.